Hello there, Khaled.
Yes, hello. Good evening, good
Sorry
afternoon.
that it took a while.
No, it's okay. I see you did it.
Okay,
Okay.
so you want to go through some of this Coriolis stuff. What is it you got now or have?
Okay. Do you have the spreadsheet open?
Okay. You going to do a screen share here or what?
Um, yeah, you can do it, but it's okay. I remember we've gone through all the calculations except the last number.
Well, why don't we just kind of start over so that it refresh my memory here? I've been working on so many different things. I having a hard time
Okay.
keeping everything
Then
straight.
you can
What
share it with me.
calculations I've made, what I haven't made. Are you going to do a screen share or?
No, I cannot. I'm on my phone.
Oh, okay. So what is it you want me to do here?
Uh, just open this spreadsheet so
So
you
you're
can.
not going to have your computer back then until Monday, is that it?
Yeah, hopefully Monday it will be back.
Well, maybe we should wait until you have your computer.
Okay. But I have some diagrams because I wanted to go into the
Yeah, well, how am
calculation.
I going to see your diagrams?
Yeah. I have my camera.
Oh, okay. Well, give it a shot. Let's see.
Yeah, if it's clear enough for you, then it would be great. Can you see my camera?
Well, I see you're a smoker.
Yeah.
Yeah, what is it with you guys from Egypt? You puff on cigarettes like candy.
Yes,
I have
especially
a
those who
couple
eat a
friends
lot.
back in Colorado from Egypt, and they're like chain smokers.
What?
I say I have a couple friends back in Colorado from Egypt, and they're like chain smokers.
Yeah.
I don't think I've ever seen a minute of their day without a cigarette in their hands.
I think the temperature also has a because when it's hot here, I don't tend to smoke as much as
Yeah.
you.
Well, I'm kind of seeing the
When you go
diagram.
to
It's a bit out of focus, but
well,
I'm not seeing everything. I mean, it looks like it's
can
might
you
be.
see?
I can see some of it. It's out of focus, way out of focus.
I don't know how to fix that.
I think it's a resolution issue too.
Yeah, okay. Resolution. I think maybe there's something I can do with resolution. Maybe if I go to my camera, uh,
Wouldn't we be better maybe doing something through Skype and then you can take a picture and just send me the file?
oh, okay. Okay. I'll take a picture now and send you Skype. I took a picture. Now I'll share it.
You sharing or going to send it through Skype?
I'm gonna send it. I'm gonna send it to Skype. If I can send it here in Google and Hangouts, but I'm not sure if I can send it in Hangouts. Yeah, I'll see if I can send it here instead of jumping between applications.
Yeah.
Ah, the share button is not working. Yeah, yeah.
Maybe
Okay.
send it through the chat on the Hangout
Ye-
here.
Yeah. Okay. Everything is slow. I even sent my
Yeah.
laptop today to send to fix it because it's been too slow, and now my phone is dying on me. Yeah. Okay. Hangouts. It's going to your hang to a previous conversation, I think. Can you open our
I've got
phone
group chat open. Is where are you sending it through? I don't see anything in group chat.
I'm
Are do you have like a YouTube window? I don't have the YouTube window open of the live stream. Is that where you're on or what?
no, I'm just on what's this thing? Hangouts. It's uploading
Yeah,
now.
I've got the chat open. It has you listed as joining, but I don't see anything posted in there. I'll just post hi Khaled here. See if you're finding it.
Okay.
I just posted to group chat.
Oh no, I cannot see it. My image is still uploading. I'll send hi.
Well, I'll tell you what. Let me just talk you through this a little bit. I kind of remember what we did yesterday. Is what you're going to basically do is you're trying to figure out what the Coriolis deflection will be. Is that correct?
Yes, when we're shooting with with different azimuths, not just south.
Yeah. Well, all you have to do is break things up into components. Yeah.
Yeah, and I do realize that this thing is very complicated. Like the
Yeah. Well, these are. I mean, what I'm doing is not strictly correct, but for short distances, the errors are so small that they you can neglect them. Is if you're
yes,
going to be okay. Let's just consider a straight north south shot along a line of latitude, a longitude. Okay,
okay,
and say you're shooting south to the equator. And you're
okay,
at some latitude. You're not at the North Pole. You're somewhere between the equator and the North Pole, and you're shooting south. Now, what's going to happen is the instant that projectile leaves the muzzle of the gun, it's going to have a lateral velocity the same as the lateral velocity of the west east direction on the surface of the earth at that point, which would be basically the tangential velocity that you have at the equator multiplied by the cosine of your latitude angle, right?
yes, yeah,
Okay, so far so good. We know at the equator we're spinning west to east at 1,035 miles per hour, or I guess what we were. Uh, let's see. You want to do metric?
yeah.
Okay, so what we're dealing.
464.
So with metric, um, the spin is going to be about 1666 1666 kilometers an hour, right?
Yeah, yeah,
Okay, so we'll put it in terms of seconds. So we're looking at 462.7 meters per second is at the equator. Okay,
yeah, yeah.
now let me get a piece of scratch paper here. Okay, so the tangential velocity at the equator is 462.7 meters per second. All right, now I think what we did is we chose at the time that our projectile was going to have a muzzle velocity of what was it, about 800 meters per second, was it?
But in the spreadsheet, I didn't count this as the muzzle velocity. I presumed it's the average velocity, just to conclude the time.
Well, I mean, in order to figure this out, you have to know all the components, and I'm just saying the muzzle velocity is independent of this lateral velocity. Okay,
Yes.
we're aiming along a line of longitude. We're shooting north to south, and the projectile has a velocity. This is its airspeed.
Yeah.
Is 800 meters per second. Just a minute. Let me make sure that that's the number. Um, okay, so we're 800. Yeah, so that works out to 2,625 feet per second. That's that's typical of a high speed rifle. Okay.
Okay.
So muzzle velocity, we'll call it 800 meters per second. Now, that projectile now is moving in space at a north-south velocity of 800 meters per. Let me think about this a second here. Okay, so what we have is, in addition to the muzzle velocity, the projectile also has a lateral velocity of whatever latitude. Is there a specific latitude that you want to choose?
It would depend on the range. Say range is 1.11 kilometers.
Where are you starting? Where is the shooter with the gun?
Let's say 40 latitude.
Which one?
40. 40 north.
40?
Yeah.
Okay. So he's at 40 degrees north and he's shooting south. Okay. Now, what kind of a range do you want?
Hold on a second. Hello, sorry, I'm back.
Mm-hmm.
So range, say 1 kilometer and 1.11 kilometers. So that would be like 1/100.
Just a minute. Just a minute. Just a minute. So, for every degree that we change with respect to the center of the Earth going along the surface, um, let's see here. And 60 degrees. So we roughly have along the surface of the Earth, we move 111.2 meters per degree.
Yeah.
Okay.
Okay.
That's using a radius of the Earth of 6,371 kilometers.
Yes.
Okay, so what's your range going to be?
To make it simple, let it be 1 kilometer point 11.
Okay, so 1.11 kilometers. So we're basically going to go 1/100th of a degree south of 40 degrees north. So our final latitude final latitude is going to be at 39.9 let me 39.99 degrees north, right?
Yes. Yes.
1/10 of or 100th of a degree less of 40 degrees north.
Yes.
Okay. Now we're not going to have much deflection at 1 kilometer, you realize, but we'll figure it out here.
We can
Okay.
put 10 kilometers.
Okay, let's put a range of 11.1 kilometers, okay?
Yes. Yes. 11.1.
All right, so we're going to end up at 39.90 degrees north.
Yes.
Okay, now our tangential velocity at the equator is 462.7 meters per second. We take the cosine of 40 degrees, which is 0.766, multiply that by the tangential velocity at the equator. And so our tangential velocity at 40 degrees north is going to be 354.4 meters per second. Well, I'll carry it to, we better carry it to more decimals since we're not shooting very far. So 354.40 45.
0.45. Okay.
Okay. 354.45 meters per second. That's our tangential velocity. Now, and we have a muzzle velocity of 800 meters per second.
Yeah.
So that projectile has a north-south component of 800 meters per second and a east-west component of 354.45 meters per second.
Yes.
Okay, so relative to someone standing on the center of the Earth and watching that bullet, or in space watching that bullet, it's going to be having a velocity of the sum of the squares, square root of the sum of the squares, right? It's going to be the square root of 800 squared plus 354.45 squared. That's relative
To his
to someone
position.
in space. Pardon?
Oh, someone in space. Yes. Okay. Yes.
Okay. Now, well, let's just get that number just for the heck of it, because what the heck?
But
Oh, I didn't
we
want to do
didn't
that.
do this. We didn't do it this way yesterday.
Well, we kind of got interrupted. I just want to just have that information here. Hang on.
Yeah. Okay. Let's try it this way. It's different. So
No,
it's
no,
good.
this is so the total velocity of the projectile, total velocity is going to be 891.8 meters per second. That's in space, relative to what someone's going to see in space.
Eight.
That
Eight ninety
that's
one point eight.
that's stationary with respect to the center of the Earth. That's
Yes.
respect to the center of the Earth. That this would be an observer moving along with the center of mass of the Earth at the center of the Earth and not rotating or anything like that, just moving along with the Earth. He's going to see um, the the projectile moving, deflecting off at 891.8 meters per second. But another way to look at this is you have the projectile moving at 800 miles per second, and you have the Earth rotating under it west to east. So there's two things. The simplest way we can do this, we don't have to use this, look at it from an observer in space, but the way we're going to look at it is from someone standing on the surface of the Earth. Someone standing on the surface of the Earth, he only knows the bullet to be going at 800 meters per second.
Like the shooter himself.
Right. Yeah, the
Okay.
shooter himself sees the bullet going out at 800 meters per second in a straight line, or not in a straight line, but uh, he knows that that bullet is going left the rifle barrel at 800 meters per second, and he knows nothing else about that. And neither
Okay.
does um, the the bullet has a lateral velocity at that point the same as the shooter. And the bullet, for the most part, is going to drift west to east along with the Earth. And if the Earth was just a moving, translating, and not rotating, that bullet would not deflect. It would just travel along with the Earth.
Yes. If the Earth was a cylinder,
Yeah,
then yeah.
yeah.
Okay.
Now, since the Earth is rotating and that rotational velocity or the tangential velocity changes as you move away from the equator or from the pole, the North Pole, the tangential velocity gets faster and faster until you reach the equator. So the velocity on the surface of the Earth is changing as a bullet is in flight moving towards the equator. And
Yeah.
the tangential velocity of the Earth is speeding up as that bullet travels. The bullet tangential velocity never changes. Once it leaves the gun muzzle, it has the same lateral component, west-east component, and that never changes.
Yes.
So its west-east component is 354.45 meters per second. So all we have to do now is figure out the time in flight. The time in flight will determine how much the apparent deflection is. Because
Yes.
as that bullet is moving, the Earth is moving faster under it. So the Earth is leading the bullet. So the bullet seems to be drifting to the west or hooking to the right as it's traveling towards the equator, right?
Yeah. Yeah. Right. I got
Okay.
it.
So the amount, all we need to look is at the starting point and the final point. We don't care what happens in between. So all we have to do is
Yes.
figure out the total time in flight, then figure out how much the bullet would have moved east or west to east, and then how much the Earth would have also moved west to east, and subtract those two to figure out what the difference is, and then that will be the deflection.
Yeah. Okay.
Okay, so the time in flight, since we've got 11.1 kilometers. And we divide by, or let's put it in meters. So we've got 11,100 meters.
Mhm.
And we divide by 800 meters per second. So time in flight is going to be 13.875 seconds.
13.58 seconds.
13.875.
Yeah.
Right?
Yes.
We have 11,000. Well, I'll figure it out. It's 11,120. So it'll be a little bit different here. Let me go 11.12 divided by 800. That's 13.9 even. Okay, let's use that. Okay. So 13.90 seconds exactly. All right. So that's our time in flight.
Yes.
Now, the initial lateral velocity at 40 degrees north is 354.45 meters per second. So we multiply that by 13.9. So the final lateral drift of the bullet will have been 400 or 4,926.9 meters. Right?
Okay.
Agree with that number?
Yeah, I just didn't write it down. 4,000.
4,926.9. That's 354.45 times 13.9,
Yes.
4,926.9.
Yes.
Just a
Lateral
sec.
lateral distance covered because of the Earth rotation at the shooter latitude.
Hang on just a second. Okay. Let's see. I just had to get back to Dean. Okay. So the lateral movement of the bullet will have moved to the east of the initial shot by 4,926.9 meters. Okay.
But the initial shooter himself moved that distance along with the laterally.
That's right. Yeah. I haven't figured out the Earth yet. I'm just saying the bullet and the shooter
Yes. Okay.
will have both moved together 4,926.9 meters
Yes.
west to east. in the easterly direction. Now we need to figure out how much did the Earth move during that same amount of time at the final position.
Yes, 39.9.
So now we got to use our 13.9.
39.9.
Right, 39.9. We take the cosine of that, multiply by the tangential velocity at the equator, which is 462.7. So now at the final position, the lateral velocity is 354.97. So the tangential velocity at 39.9 is 354.97 meters per second. So that times our 13.9 seconds gives us a movement of 4,934 we'll just call it 0.0.
All right.
4,934.0 meters. And we had 426.9. So the difference is going to be 7.1 meters. So that's the apparent deflection of the bullet at the target.
7.1. Yeah.
So
yes,
the bullet will have missed the target by 7.1 meters. It will be missing it on the right side of the target.
Mm-hmm.
It will be deflected. It will miss the target by 7.1 meters to the right of the target, as opposed to the left side of the target. On the west side of the target, you'll pass by the target 7.1 meters to the west.
Yeah. So I want to try another way.
Okay.
We subtract the difference of speed between the 40 and the 39.9.
Yeah, that'll work too. That's exactly what we do. You just subtract the speeds multiplied by the time in flight.
Yes, okay. So we can skip the step of the multiplying.
Yeah, I just took it in, excruciating detail. Yeah, you can,
Okay.
because what you have is, say, tangential velocity initial times time in flight, and then you have tangential velocity final times time in flight. When you subtract the two, you can factor out the time in flight, so you just have the velocity final minus the velocity initial times the time in flight, algebraically.
Okay.
Yeah, we can subtract the velocities multiplied by the time, or subtract the product of each velocity times time. Either way, gives you the same answer.
Okay, that's great. So I think we can move to the next step if you're not shooting exactly south.
Okay.
So first of all, I know that if from any position on the Earth, you take a flight that's 45 degrees, for example, 45 degrees from the east, like that would be 135. When you arrive your destination, uh, you cannot reverse the angle and you fly back. The arriving angle will not be 45 to the east.
Okay. Well, say we're not. So we're shooting across lines of longitude. We're not anymore along a line of longitude. So the thing is, again, we're using short distance approximations here, rather than taking into account curvature on the Earth. Is when you're shooting to the right or left of due south from the north, the the bullet is still traveling at 800 meters per second.
Yes.
And the thing is now is the latitude, the final position of the latitude will be somewhat closer to the shooter than it was shooting north-south, right?
Yes. Huh.
So we got to figure that one out. We got to figure how much shorter that's going to be. And that will be, let's say, our angle theta, or let's call it angle alpha. Angle alpha is the angle that the shooter is shooting the bullet to the, let's say right,
The azimuth, like the
pardon,
azimuth.
to
The
the
azimuth.
west. Yeah, the azimuth will measure with respect to the south rather than to the north, okay, to make it an
Okay.
acute angle.
Okay.
So angle alpha will be the azimuth measured clockwise from south.
Okay.
So now the distance along a line of longitude so that we can get what the latitude angle is going to be the uh, cosine of alpha. Well, okay, what we have to do is figure out where do you want to place the target now? You
The target would be like, say, 45 degrees azimuth from south,
okay?
and at a range of it doesn't matter anyway. We cannot make it simple. So any range, just say
Well, you
20.
can make it simple. I mean, as far as the range goes, I mean, we can do the same thing we did if you want, so that we can compare. We can use a range of 11.1 kilometers if you want.
Oh, we can make the angle to be 30 degrees, so we can have a 30-60 triangle.
Okay.
Numbers here.
So we're going to be 30 degrees off south to the west,
Yes.
and the target is going to be at 11.1 kilometers, right?
Okay. Or you can say
Well, let's do it so that we can compare. Or
let's
what do
do
you
it
want to do?
20 kilometers.
20?
Yes. So we'll have the square root of
Okay. All right. So our range is 20 kilometers. We have a muzzle velocity of 800 meters per second. We have a starting point at 40 degrees north latitude.
yes.
Okay, so that's our information, right?
Yeah.
Okay.
Starting point latitude 30. What? What latitude?
40 degrees
40. Yes.
north
Okay.
is
Yes.
our
Yes.
starting latitude, 40.
Yeah.
Okay, and we're shooting 30 degrees to the west of south
Yes.
with a muzzle velocity of 800 meters per second.
Mm-hmm.
Okay, so again, our time in flight will just be the range divided by muzzle velocity, right?
Yeah.
So we've got 20,000 meters divided by 800 meters per second. Our flight time is exactly 2.5 seconds.
Nice.
Okay, now what we have to do now, let's see.
Calculate the longitudinal, if I can call it longitudinal distance for the bullet.
Yeah, so we have 111.2 kilometers per degree of latitude, right?
111.2.
Yeah, 111.2 kilometers per 1 degree change.
Yes.
So we're moving now to a range 20 kilometers downrange. So in terms of degrees,
No, we're not. It's not 20 kilometer. We're taking the vertical component only.
no, you said the target is from the shooter 20 kilometers away when you're aiming at 30 degrees off
South.
south.
So I want to know how much south the south component traveled by the bullet, or should be traveled by the bullet, to get the new latitude.
The let me think here a second of what we're going to be doing here.
Can I see my triangle?
No, I know what you're doing here. I got to think about this a second.
Okay.
Because we're off the North Pole. I had my diagram as on the North Pole, which isn't right, of course. And we're going to aim south. Can't draw worth a darn right now. Let me try this again. Okay, we're at 40 degrees north. And we're going to shoot 30. Okay, so all right, we take the component along the radial line from the North Pole through the shooter, and we take the cosine of your 30 degrees times the range.
Yeah.
So we've got 20,000 meters, and we multiply by the cosine of 30, which is the square root of 3 over 2. So 30 times the cosine, that's 0.866 times 20. So we've got 17 or 17.3205 kilometers.
17 point.
17.32.
17.32.
Is that what you have?
I'll I'll check that.
Well, if we
So
take 20 kilometers,
yes, exactly. That's what I have.
okay,
Okay, 17.32.
okay. And we divide that into 111.2, or divide 111.2 into that to get the degree change in latitude. So we have a degree change of 0.15576 degrees, and subtract that from 40. So our final latitude is 39.844 degrees north latitude.
Yes, okay.
Okay, so our tangential velocity at that point, we take the cosine of that and multiply by our
462.
equator, 462.7.
Yeah.
So our tangential velocity now is 355.256
Okay.
meters per second. Now, over a flight time of 2.5 seconds.
25 seconds.
Pardon?
25 seconds.
25, yes. Sorry. 25 seconds. We now have a deflection of 8,881.4 meters. Right?
8,800.
8881.4
81.4 kilometers.
meters.
81 kilometers.
Meters.
81 meters.
8,881 meters.
Yeah, okay.
8.88 kilometers.
Yes, okay, okay.
Agreed?
Yes, okay.
Okay. So that is the movement of the Earth at the final position, at the final latitude.
Okay. And from the initial.
Now the bullet has an initial lateral velocity or again, we could do just subtract the velocities and multiply by the time.
Yes.
Yeah.
That's easier.
So let's just figure out the other velocity first. So we've got the cosine of 40 degrees times 46,
I have it
462.7.
354.45.
Right.
That's at north latitude.
Same as what it was before.
Yeah.
More exactly, it's 354.449. Okay. We'll take it to 3 decimals as we have it on the other one. So when we subtract 39 or 35, 355.256, 355.256, we subtract those, we get 8.0724. Or 8.072 meters per second. That's the difference. And then times 25 seconds, So
Yes.
we have a deflection of 20.18 meters, or no?
20.18. Okay. That's a deflection to the west.
Yes.
Okay. Now, 20, let's say just 20 meters to the west, but that's not what the shooter observed. You as perspective.
Pardon, you're breaking up on me. Say what now?
Those 20 meters will not be observed left to right. Now, according to the perspective of the shooter,
Yes.
along the line of shooting.
No, it'll be hooking more to the right because of the longer flight time.
Uh, um,
It'll be deflecting to the right, to the west, just like it was before when you just shot straight north south.
okay, me just to make a point.
No.
All right, so hold on. Can you see my screen?
Yeah, almost. It's still not very good.
So right here is the target. Right here is the bullet.
Just a second.
Where it's going to hit.
Here, hang on just a minute. Here, I gotta. 384, 354, 97, 354.45. Okay, go ahead. What do you have now?
Okay. Can you see this triangle?
No, it's not in focus. No, no, no. Try moving your camera back and forth and I'll tell you when you got a good image. Yeah, none of them is good.
Okay, let me try the other camera. Is it better now?
No. You got a cord in the way there or something.
Yeah, okay. Let me move it away.
I lost your. Okay, there you are.
Shit. Yeah, okay. Is this better?
Yeah, not really. I can just barely see the line.
Hold on, please. Yes.
The resolution on that camera is not very good at all.
It's I think the issue also is focusing.
Yeah.
So
Is there any way you can adjust the?
can you? Oh, I don't have much options from Hangout, but
No,
you
on
can
your camera,
draw this triangle.
can't you adjust the lens, the focus on the lens?
With digital stuff, and there's no control for it in Hangouts.
No, I mean
Okay.
physically. Can't you physically adjust the focus on the camera?
No, but hold on. I have a set of lenses, like fisheye lenses and macro lenses. Maybe they can fix it. Yeah, I got them here. Give me. I'll start with the fisheye lens because I think it
Yeah.
fixes all. Can you see it now better?
Not really. It's still way out of the resolution is just extremely poor. It's almost pixelated.
Oh, maybe because of my internet connection. So I'll try this one, and maybe I can switch to another connection.
I mean, the
Any better?
resolution is so bad. No, it's just really pixelated.
Okay, let me try the 4G instead of the Wi-Fi because I have problem with Wi-Fi today. Hello?
Oh, that's getting better. Oh, right there, right there, right there. Oh, very good. Very nice.
Okay.
There, perfect. Oh, you moved it away. Now I don't.
Yes.
There, right there, right there. Perfect.
Okay. So here's the shooter,
Yep.
and this is the line to the target,
Yep.
and the bullet will come here.
Yes, on the earth, on the surface of the earth. Yeah.
Okay. So this was 17, but this,
Wait a minute. 17.
yeah, 17.32, I think.
I got 20.18. Well, anyway.
The range was 20. Wait, let me check. I have it here.
20 was
Yeah,
20.
17. The the range.
Was
So we got
20.
17, 20 kilometers.
No, if we looked at the velocity difference was 355.256.
Oh, sorry. Yes. I got a totally different number. What was the?
The
Okay, tell me what was the shift?
the velocity, tangential velocity at 39.844 degrees north was 355.256.
Yes.
And the velocity at 40 is 354.449.
Yes, we got 20.18.
So if we subtract, we get 8.072 meters per second times 25 seconds. That gives us 20.18 meters.
Yeah. Okay. So yes. Sorry. So it's not 17. This 20.18. This lateral distance is 20.18, but this distance is difference.
Well, the
See,
thing
you can
is,
observe.
see, that's the problem. We're making approximations because, you're dealing with arc lengths and we're trying to straighten them out. And,
Yes. But remember,
what we're
we are
doing holds for, short enough distances. If you start going like hundreds of miles or something, you're going to start running
yes,
into,
will not work.
inaccuracies. You got to be more exact on how you're doing these calculations.
Yeah. So even 20 kilometer, I think it's a little bit much. But just for
Well,
the
not
sake of
necessarily. Not for 25 seconds in flight.
Mhm.
And um, it's flight time and distance downrange that makes the difference. The longer you're in flight, the more time the Earth has to spin underneath the bullet.
yes.
And then what determines the difference is how fast the bullet is traveling during that 25 seconds. The faster it travels, or the faster its velocity, the further downrange it goes, and the more the Earth deflects, or the Earth moves. So
Yeah.
basically, the important thing is time in flight. The more time you have in flight, the more the Earth will move underneath the bullet.
hmm
Now I'll have to maybe come up with a first order correction to this. Is I just use a simplified calculation to illustrate, the idea and the fundamental principle on Coriolis, but to to really get it within a high degree of accuracy for long flight times, you're going to have to um, be a lot fussier, and probably end up integrating things with calculus in order to get what the true deflections are going to be, because you're dealing with uh, a complicated surface now, and you have to look at arc lengths, because that person or the target is going to be moving actually in an arc rather than in a straight line, as we've assumed.
Yes.
Now,
So
breaking in what you're doing with triangles, you can get probably a first order correction doing that.
what's the first order correction?
Well, meaning that, you in any sort of estimations, we talk about the degree of accuracy of a estimation in terms of orders. Like if you were to do a Taylor series expansion on a function, you have things to the first power, to the second power, to the third power, and you're looking at just the first term correction, which would be a linear correction, something to the first power, and then a second order correction would be looking at the next term, where things are to the second power, and so on. The higher order correction, the more accurate the approximation is. So the first order correction is kind of like a linear term correction that you can kind of estimate with what you're doing with triangles, where you can just kind of use some simple plane geometry to give you a first correction term to the value, to get it in closer to what exactly would be happening there.
Okay.
So what is it that ultimately you're trying to do here? You want to build a calculator? You want to get really accurate, or are you just trying to get an idea of how the Coriolis works? I guess that's what we need to answer here.
Yeah, I want to get accurate on all directions, and even counting in the effect of the atmosphere
Oh
within
my.
that first order of correction. Just simple short distance like maximum 4 kilometers, because that's
Yeah,
the
well, that's
closest.
going to take some figuring. I mean, that's not going to be real simple, Cal. You're just not going to be able to use little geometry with triangles like this anymore to do that sort of thing.
For just 4 kilometers.
4 kilometers, 4,000 meters. You mean?
Yeah, that's it.
Oh, okay. Well, yeah, you could get in probably pretty close. I mean, it's not going to be, super accurate, but you could get in close enough, I'm sure. I'll have to sit and think about it a little bit.
Okay,
Is
so just to wrap up this point, if there is a person here, can you see it?
Yeah, you're talking at the same radial distance from the shooter as the label the points A, B, and C on your triangle.
A, so A is the shooter,
Yeah.
B
B,
is the target,
yeah.
C is the man that you killed by mistake.
Yeah, okay. So B and C are the same radial distance from A, is what you're
Yeah,
saying.
I think so because this angle, the angle of deflection is very small.
So let's see
So
here. We've got, I'll just draw this so you don't have to hold your camera there anymore.
so we have this here is the right angle, and what? And
Okay, A,
this
B,
here,
and C. Okay, I've got the diagram so you don't have to keep holding
oh,
that.
there's also D, the final point of the
Yeah,
of the
so we have A, B, C, and D. We
yeah.
have the distance between B and D is 20.18.
Yes.
Okay. Let's think about that a second. Okay, so the bullet's going, we're aiming the bullet from A to B. And during that time, okay, let me see. We got from A to B. So during that time, A and B
we
move
want to
together. Pardon?
we want to calculate BC.
Well, I'm just trying to convince myself what the distance that distance between BD is 20.18.
Yes.
Um, let me think about this a second. I want to make sure that that's right. A and B move together. Um, but the Earth move further. So now the Earth is there. Okay, so that's 20.18. So I guess what we could say, Khaled, is that during the flight time, the bullet moves the range. What did we say the range was there, or how much it went? It went
20, what?
yeah, that's right, 20 kilometers. Okay.
20 kilometers.
Yeah, it went 20 kilometers. So the distance,
AD will be a tiny bit more than 20 kilometers. It will be just a few meters more than 20 kilometers.
which one? A, B as in boy,
AD,
D as in
alpha
dog.
delta. Yeah.
That's what I'm trying to convince myself here of, is you're aiming
I did.
you're
Mhm.
aiming to be okay. So what is okay? Tell me what you're trying to do here first.
I presume that the angle from A to B is virtually the same as A to D.
Huh?
Can we agree on that?
A to B as in boy,
Yes.
as A. What angle are you talking about now?
The the line, the angle of the line alpha delta is equal,
Delta.
yeah, duck D.
No, describe an angle using 3 points.
Okay.
Like if I want to talk about the interior angle of your triangle, BAD, that's the angle with A at the vertex. The middle letter is always the vertex of the angle.
Okay. I'll presume that the angle BAD is
Uh-huh.
zero. It's virtually zero.
Well, yeah, it's going to be very small. Yeah.
So the angle of BDA is going to be 60.
Just a second here. Just a minute here. Our final deflection was what? It was 20.18 meters. Was that right?
Yes.
Okay, and we're shooting 20,000 kilometers. Yeah, so it's going to be about 100 or a thousandth of a radian. And a radian is about 57 degrees. So yeah, you're looking at about 6/100ths of a degree. Yeah, it's very small. Okay, now what?
So the angle BDC,
B is what? B or
as
boy
boy,
or dog? What angle?
B boy, DC.
Okay, that angle
It's going
now is what?
60 degrees.
Okay,
And we have the BCD is 90 degrees.
okay. Yeah,
And we
so you
have the
got a
length,
30, 60, 90 triangle. All right.
yes. And we have the BD distance, which is 20.18.
Yeah, so that's a hypotenuse. So the sides are the side opposite the 30-degree angle. CD is going to be half of that, which is about 10 meters.
Yes.
And the other side is going to be about 20 times 0.866, around 17 meters or so.
Yeah. So that's the perceived deflection of the bullet. How much difference left to right from the shooter.
Okay, so you're saying 17 is what he's going to see the deflection at.
Yes.
Yeah, I'd agree with that.
Okay, so that's the final line in this the first spreadsheet. It's I call it the left to right deflection.
Yeah, because I mean, what an observer sees is a will be the line swept out by a radial distance from the eye. For
Yes.
example, the distance AB is in boy will be the same distance as AC is in Charlie,
Oh yes, almost.
roughly. I mean,
Yeah.
for small enough angles, and that's what that's what a observer perceives is the side subtended by that angle. Call angle A or C, A, B as in boy, call that angle alpha. So angle alpha is very small, and what the distance as far as deflection, what an observer sees is the chord subtended by alpha. What we mean by that is the side length of a triangle that's opposite angle alpha, where it's an equal, where it's an isosceles triangle, where you have two sides being the same. That's what we perceive as a deflection distance. We cannot perceive the distance d, b as in boy, because that's at an angle from our point of view.
Yes,
It's
yes,
not, we're, that side is not always at basically right angles to our perspective. So we can't estimate really what the distance dB is from point A.
yeah. And I think now I'm going to move to just a side track a little bit to tactical. Uh, there's something I think it's called in the military the shooting ticket or range ticket. It's just a small paper where the shooter put uh, put the things that he see and write down distances, things like that. So I think that snipers that are supposed to shoot for high for long range, they have something like that that tells them the Coriolis effect for each direction would be how much.
Yeah.
Yeah,
I've never seen a sniper manual, but I wouldn't doubt that that would be the case. I'm sure they've got extensive tables in there
yeah, I think so.
that, that goes from, you know, that gives you uh, your latitude, given a latitude and an azimuth, what the corrections have to be.
Yeah, and I think latitude will not be changing because in your in a battlefield or a certain war area, you're not going to move much. So you're
Just a
going to
minute,
work
just
on
a minute. Hang on. I'm
yes.
sorry, I got an interruption there. What were you saying? No,
I was saying there will be no change in latitude tactically
change in latitude of what?
for the shooter. He will not
For the
change.
shooter and what? Between the shooter and the target?
No, for the shooter location, he doesn't change location much. So
Well, what do you
he
mean he doesn't? I mean, he could be anywhere on the earth.
yes, I mean he will make this calculations for his new post when he arrived to the battle area for his
Right.
what do you call
Yeah.
it? Yeah.
Yeah. From his position. Sure.
Yes.
Yeah. And he can shoot targets all around his position.
Yes. So it's not that hard to take account of Coriolis because I personally
Well,
uh,
like I said, I don't know how these manuals are arranged. I've never seen what kind of tables they have or anything, but it wouldn't surprise me that I don't know if they have to actually sit with a calculator or they just have tables that they look at. If you just have tables, I would imagine that you're going to have an extensive set of tables, say, um, where you're maybe divided into latitude, starting latitudes, maybe divide a table every 5 degrees or so, and then um,
every 30
and then
degrees
for
maybe or something.
azimuths then azimuths centered around that starting latitude. I don't know. I don't know how they're arranged. I've never seen them. So see, what I would think is that you would have a table, say, for 5 degrees or south degrees, um, uh, 5 degrees north or 5 degrees south latitude, and then uh, that table for that particular latitude, and then divided, say, in azimuths of, every degree or so or something, just shows you a correction. I can imagine you have like, degrees of azimuth, and then correction, one table for 5 degrees north. Now another table for 10 degrees north, the same way you'd have azimuth around your position and deflection. I don't know. Like I say, I've never seen how they um, document this stuff or have it arranged, so I really can't help you with that. I've never seen a sniper manual.
Yeah, I hope later Monday can provide some stuff.
But they could have these things divided up like in rules of thumb too. Sometimes a lot of these things distill down to rules of thumb. If you're at this latitude and you correct this much for each degree of azimuth or something, at
Yeah,
this distance. So your tables are going to have, degrees of azimuth, say on the vertical scale. Horizontal scale will be distance to target, and then at the intersection will be the deflection correction, the correction for deflection or something, or how much right or left you have to in degrees that you have to correct. I don't know. Like I say, I'd be interested in seeing one of these manuals. I know maybe Fletcher could help us out with that. He was in the military and did some instructing on some of this stuff, so maybe he has some manuals or tables he could show us to see, how the military sets these up for snipers.
yes. Um, I think the I put some average number, uh, uh, or to be exact, I took the longest shot, which was 4 kilometers or point 0.4, something like that, and they gave a specific information which was really useful. The time of flight was 10 seconds. So I I just put the 10 seconds in the spreadsheet, and the difference was was at maximum. Uh, I'm not sure. I don't have the spreadsheet now. If you can you pull it? Can you pull it up the spreadsheet? It's in the older Hangout.
No, I don't know where it is. I don't have that up.
The
I don't
Hangout that we
remember
have.
anything on your spreadsheet that I just saw a very small portion of your spreadsheet yesterday.
I put it on Drive and put the link for it in our previous Hangout in the YouTube.
Hang on a second. I gotta let Con in. Yeah, I will be looking into this more in the future when I finally get to the point where I'm going to finish up my series on Coriolis on my videos, but that's a ways off yet. What is it that you're trying to do now again? What about your spreadsheet?
Yeah, just wanting to calculate the shift because I forgot how much was it for that distance and flight time. But it was something very small. I mean, like if the target, if the man who was killed by that shot was laying on the ground, left to right shift would still kill him.
Yeah. Well, what I would do is I, I'm sure there might be some sort of a calculator out there that they use the exact equations, or at least, maybe talk to Fletcher about getting a hold of a page or two of a manual so you can compare your calculations to what the military has, so that you can verify what you're doing is correct. I mean, like I says, I've just looked at it from this very basic, simplified point of view, just to illustrate the principle to people without having to, really go into deep into equations,
Yes.
and trying to do something more exact, because that tends to lose the audience, I found.
Yeah, yeah.
So, is there anything else?
I think maybe next time we talk about the what do I call it? The perceived wind because of the atmospheric movement.
What do you mean atmosphere movement?
Well, the atmosphere is moving with the Earth.
Yeah,
So let's
but
get
there
back
is
to
no perceived wind. I mean, if it's moving along with the surface of the Earth, what causes winds is thermals and other things going on in the atmosphere, where you have independent air masses, or air masses that move independently of the atmosphere as a whole. It's still moving along with the atmosphere for the most part, but it also has some additional movements and velocities in addition to just the general um, movement as it spins with the surface of the Earth.
but if the bullet is flying from north to south, uh, when it reaches a certain point or like the end latitude, the Earth is moving underneath the bullet, and also the atmosphere is moving with that same speed, affecting the bullet.
Oh gosh. Um, oh, yeah, I don't know.
Okay, little let it be for the next time.
Oh, shoot. Yeah, I have to think on that one. Um,
Yes.
let's think on that. Hang on. Yeah, that's going to be related to the velocity of the bullet. At drag usually goes as the cube of velocity.
Oh, I have no idea how to calculate that, but what I got is a table for wind speed and bullet deflection.
Yeah, I mean, that's
That's
going to be a difficult thing, because I mean that's a function, of the profile of the bullet. Um, I'm
uh,
not sure you want to get into that sort of detail, but
no, no, no. I will not go into calculating that at all. You can see if you open the spreadsheet, the third sheet have a table, wind speeds and ranges, and how much deflection in inches for each
hmm,
range under that wind speed.
okay.
So
So you just do a lookup then on the table.
yes, do a lookup on the table and compare the I still
Yeah,
can't.
but the
What
thing is, what you've got going on here is it's more of a process. You'll have to integrate it because over the flight time and the path of the bullet, that so-called apparent wind speed you're talking about changes continuously. So you have
Yes,
to integrate it over the path of the bullet. You just can't take a beginning point and a starting point.
yes. I took the average.
Yeah, well, that's again, that's a first approximation, a first order
Yes, yes.
approximation. Yeah.
I mean, it makes different like 20% against Coriolis effect.
Yeah. Because
So
let me
yeah,
just think here a second. If you, let's say, if you have a velocity that's changing linearly with time, which happens as you are moving, the speed of the Earth underneath the bullet is changing linearly with time, right?
yes,
Because it's a r omega, omega being the angular velocity of the Earth, r being the radial distance out. So it's a linear change with position moving southward. So if you integrate that, if say the tangential velocity is omega r, and the change in r is the velocity of the bullet times time. So essentially, the tangential velocity is omega times the velocity of the bullet times time. And if you integrate that over the flight path, you get a t squared relationship. It's omega b t squared over t. So let's see, omega b bullet 2. So you got final time squared. Now the average, um, let's see, that, let me think of that. That would be the, and then we divide by the interval. Oh, why am I, my mind's not working here. So we got the tangential velocity is omega b times t, integrate that. We integrate over the interval, divide by the integral. So it's omega VB t over 2. Yeah, I guess that'll work. Um, yeah, the average velocity will get you close.
okay. So for short distances, we can conclude three things. The basic shift because of Coriolis is very small, and it also is smaller when you're shooting at different azimuth than south because of the
Right, yeah,
perceived.
because there is no Coriolis if you shoot east-west on the equator, you know.
Uh, yes, I'm just saying that the shift is less when you shoot like 45 from the south, and the perceived shift, the left right from the observer, is even less, and the wind or the perceived wind even make it more
Yeah.
less.
Well,
So
what
the
well, this
yeah,
might blow your mind. I haven't got far along enough in my Coriolis discussions to talk about this, but if um, some Coriolis is up and down, it just depends how the direction you're shooting in. Coriolis is a cross product of of the trajectory of the bullet with the rotational frame, and um, at the equator, there's no Coriolis deflection going left right, but there is a Coriolis going up down.
um if you're shooting east-west.
Mm-hmm. Yeah.
Yes, I think so because the yeah. I cannot explain it, but I get your point. Yeah.
Yeah, and it gets really complicated as you're shooting, different azimuths because you get combinations of these things occurring, you know. Whereas going a straight north-south shot, your Coriolis is horizontal plane going, deflect east-west. But as you shoot at different angles, you also get vertical components.
Mhm. And to even make it more complicated, if I wanted to integrate this wind thing, the wind affects more than we would calculate based on the average speed because the bullet at the muzzle speed is very fast, but at the end it slows, so that gives the
Yeah,
wind.
I mean, sure. I mean, once you start adding in all the practical real world aspects, the problem starts becoming intractable.
Yeah, and the accuracy to or the final product of refining these data is not going to be that much.
Yeah. Because see, when solving problems like this in the engineering field, is what we do is we start with very simplified models, and then once you get that solved, then you add more and more layers on top of it to make it more complicated. And at each step that you introduce some new aspect and parameter, then you check yourself by reducing it down, see if your equations reduce down to the more simplified model, which they have to do, you know. So you keep checking yourself. You add another layer of complication, you get it solved, then you make simplifying assumptions on that more complicated equation to see if it reduces down to the simpler models that you started with, and you kind of build up that way so that you build confidence in that your analysis is correct rather than starting out and trying to solve a problem with all the various parameters and different influences that or different things that can influence a problem. You don't want to have to try to solve a really complicated problem to begin with. You start with a simplified problem and then you add layers on it because once uh, the structure or the way you solve a problem um, basically is the same, but it gets more complicated. The equations become more nuanced as you add in more complications, but the approach is pretty much the same. So you build up confidence in your analysis is correct by starting with the simpler models and then just make them introduce complications as you go on, um, and follow your previous analysis so that you're not getting buggered up.
Yes, I kind of did the same with my sun calculator. I needed to know the what do you call it, the true anomaly of of the Earth. So in the first version, I presumed a circular orbit. In the next version of modifying these calculations, I presume that the Earth orbit is two halves of a circle with two lines connecting them that are 4 million miles. Do you get what I mean?
Yeah. Yeah.
Yeah. So and it worked fine. It gave really nice results when I compared it
Yeah.
to time.
Well, I mean, that's what you do. I mean, you don't want to jump, you know, whole body into the lake to begin with. You kind of want to stick the toe in and then go up to the knees and then the waist because otherwise a lot of these problems, real world problems, they become intractable. What I mean by intractable, very difficult to solve.
Yeah.
Um, in fact, even I can come up with really simple, what seems to be a very simple problem in the real world that is almost impossible to solve mathematically. Um, uh, it, uh, it can get very
Ugly.
difficult. Yeah, very ugly. Exactly. And um, a lot of the problems, real world problems, cannot be solved in what we call closed form. In fact, most of them can't. You have to use numerical analysis and iterative techniques in order to get solutions because you just can't do it in closed form. And that's why we make simplifying assumptions like, a spherical Earth versus an ellipsoidal Earth. You start introducing the ellipsoidal, and, and now your tangent lines and everything are not so nice, and um, you have to use calculus a lot of times to solve things rather than simple plane geometry. Dealing with spherical geometry is nice. Things always work out. That's why a lot of times, at university problems in physics, we say, assume a spherical chicken.
Yeah, this is fun. Oh God, I'm glad I'm having this hangout with you instead of going to other hangouts because I really lost patience.
I'd tell you that, what was it? Whose hangout was that? Oh, Ranty's, that guy that did the rebuttal on yours, that flat Earth guy. Oh man, was he out there?
God, I really didn't want to comment, say anything. I thought first of all to just ask a question. Did he see my my presentation, or just say no comment? But I didn't really want to hurt that guy. He did a lot of effort. It's useless, but
Well, you need to. I mean, I'm sorry, but when people spew bullshit and just are really off the rails, you have to beat on them because otherwise those that listening think that, they don't understand what the guy is saying. And they figure, well, you know, he knows what he's talking about because I don't understand it. you know?
and they don't understand also.
Yeah, I mean, oh my gosh, late last night, if you wanna hear some real crap, um, almost all night last night, Jose had a hangout with, per Schemo on there,
Oh
and I
God.
jumped on for a while, and I tell you, I think the guy is becoming mentally ill from all this discussion on flat Earth. I mean, I just could not believe what he was saying. I mean, pull it up if, Jose, posted. Gosh, Jose was on, like, for 5, 6 hours, I can't believe it. Um,
You mean Jose, not Sperskimo?
no, Jose. Jose had
Oh,
his hangout up for about 5, 6 hours, and Spurs was on there.
oh my God, that's painful.
Oh, yeah, it was horrible, and, the stuff he was saying, we were trying to talk to him about gas pressure a little bit and stuff, and the guy, you know, he's making declarations that air has no gas pressure, only water has pressure,
Yeah,
and it's just nuts.
and
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 I think he's getting a little bit mentally ill. That's the only conclusion I can come to on all this is he's been doing this for so much, he's believing his BS.
yeah, I want to ask about the term of ear popping because when I go up in even when I go uphill driving, I have problem with my ear.
Yeah.
The
Yeah, that's an
channel.
inner ear problem of equalizing the pressure. Yeah, there's little holes in your inner ear to
Yeah,
equalize the pressure, the
no,
eustachian tube.
it's not quite open or doesn't open when I need to on my right ear.
Yeah.
So my ear hurts me. I don't hear
Well,
popping.
do you ever open up your, if you try to yawn, that sometimes equalizes the pressure. If you open up your jaw, like your yawn, making a real hard yawn, that will
Yes,
equalize the pressure.
it works on the left ear, but the right ear, oh my God,
Uh-huh.
that's a problem.
I see.
So so it's a pain that I feel when I go up or go
Oh
down.
yeah, yeah. Unequalized pressure in the inner ear can be extremely excruciating pain.
And sometimes when it equalizes on its own, either the left or the right ear, sometimes I don't hear the pop-up.
Mm-hmm.
I don't hear that ticking sound. Sometimes I don't hear it, but suddenly the pain is relieved.
Yeah. Well, like I
So
say, just keep trying to open up your jaw really hard and swallow at the same time
yeah,
to try to force that to happen.
I once I used to fly motor gliders, and so one time I climbed to 10,000 feet, and when we were going down, I, I I kind of forgot to do this procedures, and
Hmm.
suddenly I felt my ear is hurting me and nothing was working because in descending it does not equalize easily. So I had to stop the captain. I said, "Please climb. I cannot fix my ears." So
Well, maybe what you're going to have to do is get yourself a helmet that you can seal around your neck and have a air valve in there that you can put an air canister, a pump, and pump yourself up.
yeah,
Yeah, I don't. I don't. I feel sorry for you on that. I know it can be very, very bad. So anyway, yeah, I mean, Spurs was making claims like they equalize the pressure inside the cabin of a jet to 5 psi, which is wrong. Everybody'd be suffering if they did that.
he
You
said
know,
what?
as you're saying that the fuselage, the cabin pressure inside a jet commercial airline is only at 5 psi, and I told him no,
Oh my
that's not
God!
right.
Why would they do
And
that?
yeah, so
Uh,
actually, the legal limit on these things is these planes are designed so that the pressure differential between the cabin and the outside is about a little over 8 psi at 30,000 feet,
uh, no,
which
I
puts the
can't.
cabin pressure at about 12 psi. About 11.7 psi is they they make the cabin pressure equal to atmospheric pressure at about 6,000 feet, which is about 12 psi.
Yes, okay, that's what I remember. I thought it's 10,000 feet, but now I think that's a more reasonable number. 6,000 feet
Yeah, it's
cabin pressure.
6,000 feet is what's recommended,
Yeah.
and then that puts you at um, uh, when you're up at 3,000 30,000 feet. That gives you a pressure differential of a little over 8 psi. Between the outside and the inside at the cabin pressure.
Yeah.
So, the outside pressure is somewhere about 3.5 psi, I think, at 30,000 feet. So, with about 8.5 psi pressure differential, that puts the cabin pressure at about 12 psi, which is the same as at about 6,000 feet.
Because they don't want to put the structure of the airplane under pressure the whole flight.
Right. Yeah. I mean, it's a judgment call, as you try to maintain uh, yeah, it's a trade-off between passenger comfort and stress on the fuselage.
Yes. Are you getting
So that's what
background
they've
noise?
settled at is that if you have about an 8 psi difference at 30,000 feet, that kind of works out for everybody, the plane and the passengers. Because you notice that, as the plane, as an airliner takes off, the inside cabin pressure is at 14.7 pounds per square inch. And then as you start climbing, they start reducing the cabin pressure. You can hear the air getting pumped out.
Yes. And, un- unfortunately for me, I was traveling a lot in military aircraft recently or this past year. So they kind of reckless working with the pressurization. So they push it up and push it down because I don't only count on my ears for this. I always, whenever I board a plane,
Yeah,
I open this application to measure the
sure.
pressure. So it's always jumping up and down. Maybe they test it on the ground before takeoff. Maybe it's a procedure for them.
Yeah.
So even before taking off, they reduce it, then they increase it again. So yeah, I have experience
Yeah.
with this.
Yeah, because all the they reduce the cabin pressure from when you're sitting on the ground at atmospheric pressure, sea level, basically. You reduce it about 4 psi in flight. You know, when you're up at about 30,000 feet, the cabin pressure is about 4 psi lower than it was at the ground.
Yeah.
Well, anyway, Khaled, I think I'm gonna move on here. Just get some things, other things done. I wish you well on your Coriolis pursuits.
Yes, and do you have a playlist for your Coriolis lectures?
No, I haven't sat down and done that. You just got to search through the videos for what you want.
Okay, okay. So I'll
There's
keep in
about
mind.
80 of them there to search through.
80?
80, yeah.
No, 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 no. You're not serious. 80
Yeah.
videos about Coriolis?
Oh, no, no, no. Altogether. I mean,
Oh,
there's
okay.
only two or three videos I did on Coriolis. I just started getting to Coriolis. I started talking about reference frames, and then I never finished up.
Yes. Okay. Do they have, or one of them have the vertical, this vertical thing?
No, I never got to that point about talking about deflections. I was just talking. I was sort of setting things up, and the basics, going through some of the basics of reference frames and other things. I've got to go back and review. That was almost a year ago now, I think.
Okay. I'll still
Yeah,
watch
I
it.
I I I started. There was one base video and I think two updates, and I never did really get to. I was going to do some videos demonstrating Coriolis on a roundabout or a merry-go-round, and also I made an apparatus that I could put on my whiteboard that would spin around, and I could show Coriolis deflection on the whiteboard that way, animated with a physical demonstration.
Yeah, that would be nice to watch.
But the one I wanted to do, I did initially, but I need to redo it as I went with my video camera and did some stuff on a merry-go-round, shooting a ball out, and but I need to redo it to get a little better video. The one I have is somewhat acceptable, but it, I would like to do it better, and that's how a lot of these things go. I tend to be kind of fussy, and then I never get the thing published because I'm trying to, you know, have a higher degree, a higher caliber presentation, and I never end up finishing it.
Yeah, well, you've been just talking about refining things, so you have to start with a crude version and then maybe prepare
Yeah,
a version
but
later.
I'll eventually get to it. I want you just keep me abreast of what you're finding out because I may incorporate what you do. And I I was going to end up the video talking about it from an engineering perspective and get into some really interesting problems. And it'll be more for students, not for general viewers. I mean, for example, um, if you want, I mean, the problems can get quite complicated for computing Coriolis effect is like in engineering, in machineries, a lot of times you have like a collar that can move up and down a straight rod. You know, like if you take a metal rod and you put a collar over it that can move up and down along that rod.
Hmm.
Now, if you can imagine, if one end of that rod now is fixed to a rotating plate,
Oh. Uh-huh.
and then this rod is spinning around on its axis on one end there, you're having it rotate as the plate is rotating, and that collar gets thrown out by the centrifugal force. Um, you know, describe the Coriolis to an observer standing on the ground to one on the plate. What is the Coriolis force? These different observers will, observe something different and will compute different Coriolis effects or Coriolis forces. So it can get rather complicated, especially like I said, when you have these collars moving up and down that can move freely on a steel rod, and then you're rotating that steel rod around, moving it around while you're on, say, a merry-go-round. It can get rather complicated.
Yeah. No, I just like to keep it simple, small distances, for just
Yeah,
for a reason because these are most of the discussions. The other day, flight earthers were
yeah.
saying that I made a shot at 800 yards, and I think 800 yards is less
Yeah.
than 1 kilometer.
Well, in the case of what I just described, there isn't any way to do it with geometry. You have to sit down and draw reference frames and vector and compute it mathematically. It becomes almost impossible to try to use your intuition and guess what's going to happen or how the forces are going to be. Because all this involves vector cross products of rotating frames upon rotating frames and linear frames, and you just have to keep track of your reference frames and the vector descriptions, and then lay it out mathematically to compute what the ultimate forces are, because it just about becomes impossible to try to diagram it out and guess what's going to happen, like what we're doing with these bullets and these simpler Coriolis demonstrations.
Uh, okay, an image just came to my mind now. There's a mathematical symbol that looks like a W, but
Yeah, it's
it's
called omega. That's a
no, no,
symbol.
no,
It's a Greek
no, no,
symbol omega. We usually use for
no.
angular velocity.
It's rotated 90 degrees. It's like a W, but or like a Z, or like a half a Z and another half a Z after it.
Huh?
It's like a W, but
Well,
it's
draw it
rotated.
out for me. Draw it out for me. What you're talking about?
Oh, I'm out. I'm
Oh,
not,
okay.
not home. It's
Well, there's an epsilon.
what does it look like?
Well, it looks like an E,
Uh, I think.
but it looks like a three. The number three with
Yes, yes,
more rounded.
yes, yes. This one. Yeah, that's the kind of equations that when I see, I just scroll up. I don't follow it. I don't know what's that. So.
Yeah, I mean, yeah, mathematically, we use a lot of these Greek symbols, lowercase and uppercase. Like you'll see in Coriolis, the capital omega, with the symbol and electrical symbol for ohms. It's kind
Uh,
of like got two horizontal feet and then a kind of like a partial circle that
oh yes,
encloses.
yes.
Yeah, that's called omega. And you'll see that a lot in the Coriolis equations. That's the primary reference frame.
Yeah. Okay, so I don't want to hold you anymore today. I'm very thankful for this discussion.
Okay. Well, have a good
Hopefully
day.
we can meet on Monday.
All right. Take care.
Okay, thank you.
All right. Later.